Hello and welcome back. Today we will have lecture 4-3, which is called a transition summary. What that means is that we are going to summarize all of the course content so far to transition to what's coming next, which will be Fourier transforms. So what we have done so far is lay the foundation for everything else in this course, where we have been working for the last couple of weeks on Fourier Series, as well as Parsifal's theorem and the power spectrum. So in summary, we have examined various types of signals and their properties, including impulse, periodic, complex exponential. We have also found the energy of power signals and also the power in signals and decibels for power analysis as well. We also examined linear time-invariant systems, which should have been a bit of a review from your AC circuits and your circuits and systems courses, and we looked at how LTI systems affect signals as shown in the following block diagram, where X of t is the input and Y of t is the output. And if we have a periodic signal, we can have the input represented as a complex exponential. We saw we can do this by using Fourier series. So then the output would be e to the j omega naught t h of j omega, where, for example, if h of j omega is a filter, we want to determine how the filter affects the various harmonic frequency present in the input x of t. We also learned that you can find the output by using the convolution integral to find the output y of t to any arbitrary input x of t, where h of t is the impulse response, and the convolution integral would be y of t is equal to the integral from minus infinity to infinity, h of tau x of t minus tau d tau, or because of the commutative property, the integral from minus infinity to infinity x of tau h of t minus tau. For the LTI system to a complex exponential, the output must have another complex exponential scaled by h of j omega. So the eigenfunction of the LTI system is e to the j omega naught t. The eigenvalue of the LTI system is h of j omega, and this is also called the frequency response, where h of j omega is equal to the integral from minus infinity to infinity, h of tau e to the negative j omega tau d tau. And we also saw that you can find the transfer function h of s and then substitute s equals j omega equals s to find the frequency response. We then discussed Fourier series, and we discussed that you can represent a periodic signal as a weighted sum of cosines and sines or complex exponentials at various frequencies called their harmonics, and that the spectrum x of k shows which frequency contents exist in x of t. So the equation we had is that the Fourier series is x of t is equal to the summation from k is equal to negative infinity to infinity x of k e to the jk omega naught t, and the Fourier series coefficient formula is 1 over t naught, the integral over 1 period t naught, x of t e to the minus jk omega naught t dt, where the fundamental frequency omega naught is 2 pi over t naught. So here we show a graphic of e to the j omega naught t x of k, where you notice every increasing harmonic is a different sinusoid, and they're all scaled by some value of x of k, where the DC value would be multiplied by x of 0, and then the first harmonic would be scaled by x of 1, the second by x of 2, and the third by x of 3, and so on. Always think about your cover page for your study guide, which is an example of summing those harmonics to get a square wave. So then here we have a plot of the spectrum x of k, which shows the frequency content in x of t, where each harmonic, omega naught, 2 omega naught, 3 omega naught, etc., has a stem plot with its value of the Fourier series coefficients x of 0, x of 1, x of 2, and so on. We also looked at some properties of Fourier series, such as Parsifal's theorem or power conservation, where power in the time domain would be 1 over the period, the integral over 1 period, the magnitude of x of t squared dt, or in the frequency domain, the summation from k equals negative infinity to infinity, the magnitude of x of k squared. We also looked at Hermitian or conjugate symmetry if x of t is real, which states that the magnitude of the frequency content is even and the phase for the Fourier series coefficients is odd, or in other words of stating that x of k equals x conjugate of negative k. We also found the cosine form for the Fourier series for real x of t as x of t is equal to x of 0 plus the summation from k equals 1 to infinity, 2 times the magnitude of x of k, cosine k omega naught plus the angle x of k. And now we can find the output of a linear time-invariant system that has a frequency response h of j omega, where if the input has a fundamental frequency omega naught, y of t is equal to x of 0, h of 0, plus the summation from k equals 1 to infinity, 2 times the magnitude of x of k, h of jk omega naught, that is the frequency response evaluated at the fundamental frequency of the input, cosine k omega naught t, plus the angle x of k, plus the angle h of jk omega naught. So this concludes lecture 4-3 on the transition summary. On to Fourier transforms.